Hi everyone, this is a video on exponent rules. So when we talk about exponents, you've probably seen them before. If I wrote something like x to the second power, that really means x times x. And if I wrote, x to the third power, that would mean x times x times x, right? So the exponent, right, the part up here, right, which we call the exponent or the power, tells you how many times you're multiplying that variable or whatever the value might be by itself, right? So there's two x's here. Here the exponent is 3, so you see 3 x's there. And then generally, right, so if I said in general, if I wrote x to the n power, where n is some positive whole number, that's equal to x times x times x times times x. How many times you see it? Well, it's n times. It's the same number of times as the exponent. It's just a way of writing it generally. It's not something that you really need to worry about too much, just understanding that the number you see is the power, right, or the exponent is telling you how many times you're multiplying that value by itself. We call this value here x the base. So we raise a base to a power or a base to an exponent. So exponents have very specific rules that go along with them. The first rule we'll talk about is called the product rule. For exponents. And when we say product, remember that means multiply. So I'm really talking about if you're multiplying two things with the same base. So if I have x to the m times x to the n power. So what I'm really saying is I have two bases that are the same with different exponents on them. M and n are positive whole numbers as for right now. They could really be any numbers in general. And this will be equal to, what you do with this is you actually add the exponents here. So this equals x to the m plus n power. Now, let me show you why that's true. Suppose you had x to the third power times x to the fourth power. According to the rule I just told you, the base is x, the base is x, the base should stay x, and then you add the exponents 3 plus 4, which makes that x to the 7th, right? So I'm getting x to the 7th by just adding the 3 plus 4 together. And that's fine. The reason the rule works is that if you think about what x to the third really means, that really means x times x times x. If you think about what x to the fourth really means, it means x times x times x times x, right? 4 times. So how many are there total here? Well, there's 1, 2, 3, 4, 5, 6, 7 x's being multiplied together, which means this is x to the 7th power. So the reason the rule works is that really what you're doing is you're adding up the number of x's you're multiplying by itself. So you wouldn't want to write this all out every time like I just did here. You want to use the rule as a shortcut because as soon as these exponents get large, it's easier to work with if you just know the rule where you add the exponents together. So let's just work on a couple examples. So suppose I had, I'll call this letter A. If I had 3 to the 4th power times 3 to the 6th power. Now, you got to be careful here. Remember in this rule, the base was x, the base was x, the base stayed x. Here we have the base is 3, the base is 3, the base stays 3. Do not multiply your bases together. Remember, we're talking about the total number of 3's that are being multiplied, so the base should stay 3. So the base is 3, stays 3. You have 4 plus 6 now is the exponent, so it's 3 to the 10th power. And later on we'll simplify this using our calculators, but for now I'll just keep it in exponential form as an exponent. Next example, if I had 4 to the 6th power times 4 to the 2nd power. Again, here your base is 4, your base is 4. So the bases need to match. That's what the rule really says. So 4 to the 6th times 4 to the 2nd, we know the base stays 4. the power, you add them together because you're multiplying, so 6 plus 2 gives you 4 to the 8th power. How about this one here? If I had 5 to the 3rd power times 5. Now the key with this one is understanding the bases are still both 5, so you know the base is going to be 5. When you see 5 to the 3rd times 5 to the exponent on 5, remember, if you don't see an exponent, is always the first power. It's not a 0. Now this is 5 to the 1 power is 5. So how do you handle this? Well, you add the exponents because we're multiplying two things with the same base. So 3 plus 1 gives you 5 to the 4th. Now if you weren't sure what 5 to the 4th is, you could do this on your calculator. We'll talk about it a little bit later, how you would do that, but 5 to the 4th power means 5 times 5 times 5 times 5 equals 625. And eventually you do want to leave it in that form as a number, but for now we'll leave it exponential just so we see the rule. Let's make sure we understand what to do if we have something like this. If I say 2 to the 3rd power times 3 to the 2nd power, these bases don't match. Remember the rule that we had above says the bases both have to be the same for this rule to work. So you can't just multiply the bases together, and you can't just add the exponents. You actually have to treat them individually. In other words, we know 2 to the 3rd, if you think of it as 2 times 2 times 2, 2 to the 3rd is 8, times 3 to the 2nd power means 3 times 3, which is 9, then 8 times 9 equals 72, and that would be the answer. Keeping in mind that when you look at this, you're really, following your order of operations. You're doing the exponents first, then the multiplication. And maybe we'll look at just one more here. If I said, for letter E, if I had z to the 90th times z to the 10th power. Again, the bases match. Z is the base, z is the base stays z. Then 90 plus 10, remember you're adding, gives you z to the 100. And that's why it's important to know the rule. So on all of these, the rules applied except for this one here. Right? The rule does not apply. And that's because they have different bases. So in order to use this rule, you need the bases to be the same. It's going to be true for a lot of the rules we take care of right here. Alright, the next exponent rule we'll talk about will be the quotient rule. For exponents. The quotient rule is actually very similar to the product rule. Quotient means divide, so I'm really saying if I divide two things with the same base. So if I had x to the m over x to the n, you might be able to guess what's going to happen here. We're dividing two things with the same base, so what do you think will happen with their exponents? We really will be saying m minus n. We subtract them. Alright, so when you're dividing two things with the same base, you subtract their exponents. It's a rule to know. Again, I'll show you why. If I was thinking of something like x to the 7th over x to the 4th power, according to the rule I just did, right, this should equal the base is x, the base is x, the base stays x. Don't try to cancel those out, right? The base stayed the same. And then you do 7 minus 4, which gives you x to the 3rd. And we know that's the answer based on what the rule says. Here's why it's true. If I wrote x to the 7th over x to the 4th, so same problem. But instead I wrote it out as, x to the 7th meaning x times x times x 7 times, right? So 1, 2, 3, 4, 5, 6, 7. Over here, x to the 4th means x times x times x times x. Remember, you're allowed to cancel in a fraction as long as you have the same factor in the numerator and denominator. So I can cancel one of these x's with one here with one here, one here and here, and then one here, one here. So what's left? Well, x times x times x, that's x to the 3rd. What's left in the denominator here? If you cancel everything out, don't put 0. It's actually all over 1. So it's x to the 3rd over 1, but simplifying that, anything divided by 1 is just itself, so you get x to the third. Another way you might see this, just so you know, is that you might see if we wrote x to the 7th over x to the 4th. They write the one with the higher power as, you know, the sum using the one with the lower power. So they might write x to the 7th as x to the 4th times x to the 3rd, because you know 4 plus 3 gives you 7. That's what I mean by the sum. So you have a product here, but then you're adding 4 plus 3 to get you 7. So I'm picking the 4 because 4 was in the denominator. And then this is over x to the 4th still. And then I know the x to the 4th will cancel out. And that just leaves me with x to the 3rd. So any of these ways is okay. You should know the rule, though. The rule is what's really the most important. This first one we did. These are just reasons why it works out. So we'll do a few examples simplifying these. Right, so now we'll simplify a few examples. So if I said to simplify, and that's typically what the directions will be. For this first one, 4 to the 5th power over 4 to the 2nd power. When you look at this, you should notice right away they have the same base, which allows you to use our rule from above. And when I go to divide things with the same base, remember the base stays the same. Don't cancel those out. So 4 is the base, 4 is the base, 4 stays the base. And then 5 minus 2, remember, is subtraction, gives us 4 to the 3rd power. The way you're getting that, remember, is just 5 minus 2. And if you wanted to evaluate 4 to the 3rd power, you could do that using your calculator. That's equal to 64. All right, let's try another one. If I had 7 to the 4th power over 7, keeping in mind what this means, the bases are both 7, so you know the base is going to be 7. And then this is a power of 4, and the power on the 7, remember, is really a 1. So 4 minus 1 makes us 7 to the 3rd power. And if you were to evaluate 7 to the 3rd, you could do it on your calculator. It comes out to 343. Eventually we'll be evaluating like we did here at the end. I just want to make sure that you know the rules first. If I had this, y to the 28th power over y to the 12th power. Again, the base is y, the base is y, the base should stay y. And remember, division of things with the same base means you subtract their exponents. 28 minus 12 gives you 16, so we have y to the 16th. All right, so now we'll use that rule to help us come up with the next rule that we're going to use. So if I gave you this example here, I said let's simplify x to the 5th power over x to the 7th power. According to our rule, the base is x, the base is x, the base would stay x. And then when we do subtraction, remember, you always have to do the one that's in the numerator minus the one from the denominator. So it's 5 minus 7, which gives us a negative 2. So you x to the negative 2, again, that's because we're doing 5 minus 7. The order matters. So if I say that, you know, we have x to the negative 2, that's fine. We haven't had a negative exponent before here. But you may want to write this using only positive exponents, because that's typically the way we're going to see it. So if I was to write x to the 5th over x to the 7th, just talking about it in the ways we've seen previously, I could write this as x times x times x times x times x. 5 of them, right? Because it's x to the 5th power. Over x times x times x times x times x times x. 1, 2, 3, 4, 5, 6, 7 times. And we could cancel out, you know, common factors from the numerator and denominator. So that one will cancel here. This one with this one, this one with this one, this one with this one, this one with this one. And, you know, if I cancel everything in the numerator, remember, if you cancel everything, there's really a 1 there. Don't forget that. You need that 1. You end up with 1 over, and down here, x times x is x to the 2nd power. Well, we got 1 over x to the 2nd power here, and we have the same thing being equal to x to the negative 2 power, right? They started the same, x to the 5th over x to the 7th. They came out to different things. What that tells us is, let's say, therefore, x to the negative 2, this must be equal to 1 over x squared. Because what it's really showing you is that, right, if I started with two things that are equal and they end up equaling to different things, those two different things must be equal to each other because they're equal to the same original piece. And that really helps us get our next rule, which is the negative exponent rule. I'll write it out more formally, but it kind of follows from what you just saw there. So the negative exponent rule tells us if we have x to the negative n power, right? So if you have a negative exponent on your base, you can rewrite that as 1 over, and then move the base to the denominator, and then you make the exponent a positive value, right? That's really what happened here. X to the negative 2 is equal to 1 over x to the positive 2. So our negative exponent rule really gives us a way of writing our answers only in positive exponents. From this point forward, all of our answers are going to want to be written in only positive exponents after we simplify. So if you don't simplify completely, meaning you don't write it with only positive exponents, then you won't get full credit. So let's talk about simplifying some of these. So if I said to simplify, and the first one we'll look at, I'll say y to the negative 8 power. Well, we see a base to a negative exponent. That tells us I can rewrite it with 1 over, keep the same base, so the base stays y, and then the exponent becomes positive 8. And that's it. You've simplified because you have an answer that has positive exponents. If I said, I'll just letter B over here. If I had 3 to the negative 2 power. Well, keeping in mind the negative exponent tells you you're going to write it 1 over, and the base stays 3, right? So the base stays the same always, and the power becomes a positive 2. And if you wanted to simplify this further, we can evaluate that exponent now. We end up with 1 over 3 squared, which gives us 9, so it's 1/9. Important thing to notice here, you can't just do 3 to the negative 2 right away and say, oh, it's going to be negative 9. Sometimes people make that mistake. The exponent doesn't tell you about the sign of the number. It tells you about where it's going to end up. It's telling you that the base is going to end up in the denominator, right? So it's telling you to move it to the opposite part of the fraction. If you think of this as being in the numerator, moves it down to the denominator, makes the exponent positive. The sign of the exponent has nothing to do with the sign of the number. So if you have a numerical base and you have a negative exponent, you have to first rewrite it with a positive exponent, then evaluate. Kind of like what we did just there. So let's do a couple more like that just to make sure we see it. If I said we had negative 4 to the negative 3 power. Keep in mind what the base is here. The base is negative 4. That whole thing is the base because it's in parentheses, so that exponent's acting on the whole thing that's in the parentheses. So I want to rewrite this and says a negative exponent as 1 over. The base is still negative 4. The negative on the base doesn't tell you anything about the direction. That's just a sign of it. The negative on the exponent told you to write it as 1 over. Keep the base the same, and you make the power positive. So it's 1 over negative 4 to the positive 3. Once you have that, now you can evaluate this further. This ends up being 1 over. Now remember, a negative number to an odd power is always going to come out negative. So you end up with negative, and then 4 to the third is 64. So you got 1 over negative 64, which is fine if you left it like that. More often than not, you probably will see it with the negative right out in front, negative 1 over 64. Remember, for a fraction, the negative can be in the numerator, denominator, or right out in front. They're all equivalent to each other. Sometimes people make a mistake there and they try to put 2 negatives in there. Remember, there's only 1 negative in the entire fraction. So either in the top, the bottom, or right out in front. Numerator, denominator, or right out in front. If I did this one here, for letter D, if I wrote negative 6 to the negative 2, keep in mind we're trying to figure out what the base is here. The base in this case is just the 6. The negative in front isn't acted on by the exponent because there are no parentheses. So the exponent's only acting on what's directly before it. So this negative in front, remember, stays in front as that negative. 6 to the negative 2, the negative exponent tells you to write it as 1 over, and then 6 to the positive 2. So if you're evaluating it, the negative in front still stays in front. So you got negative 1 over, now 6 squared is 36. So you got negative 1/36. Right? Make sure you leave this as a fraction. We'll do a couple more. Suppose I had negative 3 to the negative 4 power. So first question you should ask yourself is what's the base? And in this case, the base is negative 3. And it's being raised to the negative 4 power. The negative exponent is telling me to write it as 1 over. The base stays whatever it was, stays negative 3. Make sure you put those parentheses around it. It matters. And the power becomes positive 4 on the base. Once you've rewritten it in that form, now you can evaluate. You have 1 over a negative number to an even power. Remember, that's always going to come out to a positive because an even number of negative signs, you multiply them together, become a positive. So negative 3 to the 4th power, we know it's going to be positive. 3 to the 4th power is 81. You can evaluate that part in your calculator. You can't evaluate it at this step. You have to do it once you're here, when you've written the power as a positive. And we'll do one more like this. So if I have negative, and then I have negative 5 in parentheses after that first negative, and then raised to the negative 3 power. Let's talk about what's going on here. First off, the base for this is just the negative 5. This negative in front is not acted on by that exponent. So the negative out in front, remember, stays out in front. The base here we said is negative 5, because that's what's being raised to the power. So we're going to have 1 over, because the negative exponent tells you to write it as 1 over, and the base is still negative 5 in parentheses, raised to a positive 3 power. And then when you evaluate this, you'll have negative 1 over, here this is negative 5 to the 3rd. A negative to an odd power, remember, stays negative, because it's an odd number of negative signs, so it's going to stay negative, and it's negative, and then 5 to the 3rd would be 125. So you got negative, and then 1 over 1, negative 125. So a negative divided by a negative really forces this to become a positive 1 over 125. Right? So the negative divided by a negative makes that a positive there. Right? Or you can think of it as multiplying two negatives together if you move that negative sign up. The next rule we'll talk about really will be based off of what we're going to talk about with division, but it's called the zero exponent rule. The zero exponent rule says for any base, and it's really any base not equal to 0, x to the 0 power equals 1. So that's a zero exponent rule. Now, let me show you why. Alright, so if I said to simplify x to the 3rd divided by x to the 3rd. Well, if you're thinking about this how we've talked about fractions in the past, we have the same thing in the numerator and denominator. The same factors cancel, dividing out to a 1 over 1, so this equals just 1. But you could also have noticed that if I have x to the 3rd over x to the 3rd, I'm dividing things with the same base. When I divide things with the same base, remember what happens. The base stays the same. And then you subtract the exponents. Well, 3 minus 3 would give me x to the 0 power. But if these two things started as the same thing, then they're equal to different things. Remember, these would have to then be equal to each other. So then we know that x to the 0 equals 1. And that's our rule that we just talked about for the zero exponent rule. So any base to a power of 0 will always equal 1. That's something you should know. It's not necessarily a difficult rule, but a lot of times people make mistakes with it because they get a little confused. So we're going to do a few of these. So for the first one, if I said I had y to the 0 power. So the base is y, it's being raised to the 0 power. Well, that equals to 1. If I said I had 5 to the 0 power. Again, the base is 5 to the 0 power, it's just 1. Doesn't really matter what the base is, right? If I said 237 to the 0 power, still equals 1. I could write 5x and then in parentheses to the 0 power. Now keep an eye on this part. The base here is 5x, the whole thing, because it's in the parentheses. The whole thing is being raised to 0 power, so this whole thing equals still 1. That's different than if I wrote this. If I wrote, for example, E, 5x to the 0 power. It sounds the same when I say it out loud, but if you don't look where the exponent is, right, that 0 only applies to the x. So it doesn't apply to the 5. So when you look at this, the 5 out in front stays 5 out in front. The x to the 0, that part is equal to 1. Remember, when you have two things next to each other, it means you're multiplying them. It just means 5 times 1, which equals 5. What if I wrote this? If I said negative y to the 0 power. Well, negative is not acted on by that 0 power, right? The power is only acting on the y, so it's directly before it. So the negative in front stays in front, almost like a negative 1. And then y to the 0 power, well, that part's 1. So you have a negative times a positive 1, which makes this negative 1. That's different than if I wrote this. Sounds the same, but it's different. Negative y to the 0 power. In this case, the 0 power, because these parentheses, acts on the whole thing that's inside of there. So negative y to the 0 power. In this case, the whole thing is to the 0 power, the whole base to the 0 power, so it just equals 1. Alright, so negative exponent rule, make sure you're paying attention to what the base is. The base to the 0 power always equals 1. That's a rule you should know. The next rule we have is the power rule. For exponents. And the power rule basically says if I have some base x raised to some power m, and then that whole thing is raised to a power n, right? So the power being raised to a power, the way you handle the rule is that when you have a power to a power, you multiply those together. So you get x to the m times n power. Now I'll show you why, again, like I have in the past, why it works. Suppose I had x to the third power being raised to the second power. According to the rule, this should be x to the 3 times 2, which makes this 6. Right? This is using the rule here we just talked about. Now, if you didn't use the rule, right, starting with the same thing, x to the third squared, you have to remember that x to the third squared really means x to the third times itself, right? That's what something squared means. It means multiply it by itself, right? So x to the third times x to the third. Well, when you multiply two things with the same base, what do you do with their exponents? You have to add them. So then this would be 3 plus 3 gives me x to the sixth. So it's the same answer. So it really gives you a shortcut way of getting there, right? So if you have a power raised to a power, what it's really saying is you multiply those exponents together, keep the base the same. So we'll do a few more examples. I said to simplify. Y to the fourth to the 12th power. According to our rule, right, it says when you have a power raised to a power, you keep the base the same. So the base here is y, it stays y. Then you multiply the powers together. What's 4 times 12? Well, that's 48. So you get y to the 48th. What if I said I had 2 to the third to the 6th power? First off, identify the base here. Sometimes we get thrown off because there's too many numbers. The base here is 2. The power of 3 and then to the power of 6. Remember, when you have a power raised to a power, you multiply those. So 3 times 6 is 2 to the 18th. And we'll look at one more like this. If you had, let's say, 3 to the 5th power, and then that's getting raised to the -7. So there's a couple ways you can approach this. The way I would approach it is probably using our power to a power rule. So identify the base. The base is 3. The power to a power, we have 5, and then times -7, so that makes it -35. Now remember what I said earlier, you can't leave things in the form with a negative exponent anymore, because we want only positive exponents to be simplified completely. So a negative exponent on the base tells me to write it as 1 over, and then move the base to the denominator. So we have 3 in the denominator. The negative on the 35 goes away, and it just becomes a positive 35, right? Because the negative is giving you the direction of writing it as 1 over, moving it to the denominator, and making the exponent positive. So you have 1 over 3 to the 35th power. You wouldn't want to put this in your calculator. You'll get a very, very small decimal number. It'll be pretty close to 0. The next rule we'll talk about is the expanded power rule. And in this rule, we'll have a times x over b times y, all raised to the, I'll say, n power. So you have something that's being multiplied or divided, and it's all being raised to a power, right? So this doesn't apply to addition and subtraction inside. It's only multiplication or division inside. And what the expanded power rule says is that you're allowed to bring that power to each of these factors that you see inside. So you can write this as a to the n, x to the n, over b to the n, y to the n. So that exponent of n goes to all of the factors on the inside. That's the expanded power rule. It applies to only multiplication or division. So even if you just had the numerator, the a times x to the n power, then the a to the n and the x to the n would hold. If you just had, a over b, then it would just be a to the n over b to the n. But it only applies if there's multiplication or division inside the parentheses. Addition or subtraction, this does not apply. It does not work the same way. We'll do a few examples. So if I said to simplify something like this, if I had 3x to the 4th squared. Well, basically what that means is take that power of 2 and bring it to each of the factors inside. Don't forget that this coefficient, that 3, should be raised to the power of 2 as well. It's not just variables. The constants or the coefficients also get raised that way. So we have 3 to the 2nd power times x to the 4th to the 2nd power. Well, 3 to the 2nd power, now you can evaluate that. That's 9. X to the 4th to the 2nd power, that's our rule for a power to a power. Remember, you multiply those, so it's x to the 4 times 2, which would be x to the 8th, so the whole thing is 9x to the 8th. Take a look at another one. If I said I had let's say parentheses negative 4x squared y to the third, all raised to the third power. Remember that power can be brought to each of these factors inside, including the negative 4. So this would be equal to negative 4 to the third, x squared to the third, and y to the third to the third. Alright, so you're raising each of those to the power. Because remember, this because we have multiplication inside, you're allowed to do that. And then we'll evaluate each piece of this. Negative 4 to the third power, a negative number, right, to an odd power stays negative. So this is negative 4 to the third, which is 64, so negative 64. X squared to the third, remember how this works, power to power, you multiply, so it's x to the 2 times 3, which makes it x to the 6th. And then y to the third, that's y to the 3 times 3, which makes it y to the 9th. And that's your answer. Be very careful here. Sometimes people see a negative in front and they try to move it to the denominator. Remember, you only move it to the denominator if it's a negative exponent. This exponent, this negative in front is not an exponent. It has nothing to do with it. It's actually the sign of the number, so you leave it alone. How about we look at this one here? If I have negative 3x, y to the negative 5, all raised to the negative 2 power. Well, that's equal to, first off, I would bring that negative 2 exponent to each piece, right? So you have negative 3 to the negative 2, make sure you have parentheses around it. You have x to the negative 2, and you have y to the negative 5 raised to the negative 2. And then you want to evaluate this like we had before. Now when I say negative 3 to the negative 2 power, remember the negative exponent, I have to rewrite it first. I can't just work with it in any other way. So I have to write this as 1 over, and then a negative 3 is the base to the power now becomes positive 2. You have to do this if you have a number inside here being raised to negative power. For a variable, like here I have x to the negative 2, that's just going to stay x to the negative 2 for now. We'll move it around in a minute. And then here, y to the negative 5 to negative 2. When you have a power to a power, you should multiply those together. So this becomes y to the negative 5 times negative 2. A negative times negative makes that a positive 10. Now, we want to write this as a single fraction if we can. Keeping in mind, this is 1 over negative 3 squared. A negative to an even power will make it positive. 3 squared is a positive 9. X to the negative 2. Well, that's really 1 over x to the positive 2. Remember, we learned about the negative exponent rule. You make it as 1 over to keep the base, make the exponent positive. And then y to the 10th, well, that's not a negative exponent, so it'll stay where it is as y to the 10th. You can consider that to be in the numerator because it's really like over 1. We don't usually write it, but just so you can see it in this case, right? This is really over 1. So how do you multiply fractions? Straight across the numerators, straight across the denominators. So the way it works is if you have a positive exponent on anything, it's going to be in the numerator because it's always over 1. So we got 1 times y to the 10th is y to the 10th. Down here we have 9 times x squared times 1 is just 9x squared. And now we have all positive exponents. We've simplified completely. All right, we'll look at one more. If I said I had negative 3y squared over 2x to the 5th, and that's all raised to the 4th power. So, in doing this, because we only have multiplications and divisions in there, you're allowed to bring that power to each piece, remember. So I can write this as negative 3 to the 4th. Y to the 2nd to the 4th over 2 to the 4th. Don't forget to bring it to the denominator. Sometimes people leave that off. And x to the 5th to to the 4th. So you bring that power of 4 to every single factor in here. Sometimes people think of it almost like distributing. It's not distributing, but it's the same type of idea where you're bringing it to each piece. Evaluating this, negative 3 to the 4th power and negative to an even power, remember, is going to be positive. 3 to the 4th is 81. Y squared to the 4th, when you have a power to power, when you multiply, so it's y to the 8th. And it's over 2 to the 4th, which is 16. Then x to the 5th to the 4th, power to power, you multiply, is x to the 20th. Now, you should check to see if any of this reduces. If it didn't reduce at the beginning, then it's not going to reduce here. Like 81 and 16 don't have any common factors. But if they did, you would want to reduce that fraction down. All of our exponents are positive. You know, everything's been reduced, so we're okay here. So, the main thing to know is to simplify completely, you need the following. Alright, so this is how you'll know you're done, because sometimes people have a hard time knowing when to stop. Alright, so to simplify completely for exponents. First, say at most one of each variable appears in your final answer. So, in other words, you know, if you have more than one variable that's got the same base, right? So if you have, you know, an x in the numerator and x in the denominator, or, you know, two of them next to each other, you can use multiplication or division rules to simplify that. The next thing you need to know is no negative exponents can appear in your final answer. So at the end of the problem, if you have negative exponents still, that means you haven't simplified completely. And we'll talk more about that in a little bit. And then all coefficients, meaning the numbers in front, must be simplified. Completely. So those numbers in front, you know, if they still reduce, you should be reducing them. Sometimes they will, sometimes they won't. But you need to know if they do or not. So we'll do a few more examples here because, you know, I think it's important to see a couple more of these. So if I said to simplify, and the first one we'll look at is eight x to the third y to the fifth over 4x to the third y to the second power. And that whole thing raised to the third power. The first thing I would suggest to do is to, you know, split this up with the inside, talking about the coefficients over the coefficients and the same variables over the same variables. You don't necessarily have to show this every time, but it might be helpful to split it up this way just for now. So if I had, you know, 8 over 4, and then you have x to the third over x to the third, and then y to the fifth over y to the second, and this whole thing is to the third power. I'm going to simplify the inside first. You could have brought the 3 to every factor like we did earlier, but it's easier to do that at the end. In doing this, in these parentheses, 8 divided by 4, well, that just becomes 2. x to the third over x to the third, well, that really cancels to, 1 over 1, which makes this just 2 times 1. And then you've got y to the fifth over y squared, which makes this y to the 5 minus 2, y to the 3. This whole thing is raised to the third power on the outside. So basically I just simplified the inside completely. Remember, it's multiplication between these because they're all written next to each other. So this ends up being 2 times 1, so it's just 2 y to the third, all raised to the third power. And now I'll use our rule that says that, if I have things that are being multiplied inside of the parentheses raised to a power, I can bring that power to each piece individually. So we can say this ends up being 2 to the third power times y to the third power, and then evaluate. 2 to the third is going to be 8. Y to the third is y to the 3 times 3, and the exponent is y to the 9th. 8y to the 9th, that's your final answer, right? There are no negative exponents. Your coefficients were simplified completely, and there's only one of each variable showing up. If you had brought the 3 through at the very beginning to each factor, you would get there, but the numbers would get quite large as the coefficients in front. And you still simplify down to the same place. It's just making it a little longer to go through it. Taking a look at the next example. If I wrote, this is 4x to the third, y to the 9th, over 16 x to the 7th, y to the second power, this whole thing squared. And when I do this, first I will simplify the inside like I did a second ago. So I have 4 over 16, coefficients over coefficients, and then I'm going to do the same base over the same base. So x to the third over x to the 7th, y to the 9th over y to the 2nd. This whole thing is raised to the 2 power on the outside of it. And then we'll simplify in here. 4 over 16, remember it's a fraction that reduces to 1 over 4. Make sure you reduce that properly. Don't put just 4 there, right? 4 divided by 4 in the numerator gives you 1. 16 divided by 4 in the denominator gives you 4. X to the third over x to the 7th. We use our subtraction rule because we're dividing, so we subtract the exponents. 3 minus 7 gives us negative 4. Y to the 9th over y to the 2nd. Well, that's 9 minus 2 makes us y to the 7th. The whole thing on the outside raised to the second power. And then, I'm going to simplify the inside of what's going on here. So, one way of thinking about this, and I'll write it out in a second, is that the negative exponents are going to go to the bottom and the positive ones will stay in the top of the fraction. So you really end up with, 1 times y to the 7th over 4 times x to the now positive 4 raised to the second power. If you're not sure how I got that, what I'm really doing is I'm just saying the inside of this will be 1 over 4 times 1 over x to the 4th times y to the 7th all squared. And if you remember from earlier, when I multiply these out, this y to the 7th is like over 1. So you multiply the numerators together, you're just going to get 1 times y to the 7th, which is just going to be y to the 7th. If you multiply the denominators together, 4 times x to the 4th, you'll have 4x to the 4th. So if you see a negative exponent after you've done that, you can move it to the denominator. And you could do that right away. So this is really equal to y to the 7th, because 1 times y to the 7th is just y to the 7th, over 4x to the 4th, the entire quantity squared. And then, you can do each piece individually. Y to the 7th squared. Don't forget to do the coefficient. 4 squared and x to the 4th squared. Evaluating these, you get y to the 7 times 2 is 14 over 4 to the second power. Remember, this is now you're not raising a power to power. You're actually doing the exponent. 4 squared is 16. Don't put 8 there. And then x to the 4th squared. Now we have x as the base. Power times the power. 4 times 2 gives me 8. And then you are simplified completely, making sure you know that you have one of each variable showing up. The coefficients are reduced completely, and you have only positive exponents. All right, the next set of examples I just want to show you so you understand what to do when you're multiplying two things with exponents together. So sometimes you might see things where you have to simplify. And they have a product. So if I said for this first one I had, let's write it out as in parentheses 4x to the third power y to the second power, all raised to the third power, times x squared y. So first off, you need to be able to get into here before you can multiply these together. So you can't get into here until this exponent on the outside is taken care of. So, you know, we have multiplication inside of these parentheses, so that tells us we can bring the exponent to each piece inside. So you really have, you know, 4 to the third, x to the third, and y to the second, to the third. And then this part still can be times x squared y. Now simplifying this, 4 to the third is 64. Now if you could see that right away, you could have just written it right away. You don't necessarily have to show that step. X to the third, remember multiplying when you have power to power makes this x to the ninth. Again, if you could just see that right away, you could just jump to this step. Y to the second to the third, y to the 2 times 3 is y to the 6th. That's using our power rule. Power to a power. And then times, now I'm going to drop the parentheses here because anything with parentheses multiplied by something is all being multiplied together. We can write this as times, you know, x squared y. So once I've done this, you know, I'm not simplified completely because I have more than one of each variable showing. You really can think about, okay, if I multiply together, I can multiply same bases with same bases. So 64, well, that's 64. There's no other coefficients. We have x to the ninth times an x squared. When you multiply two things with the same base, remember this is multiplication, you add their exponents. So this is x to the 9 plus 2, which makes it x to the 11th. And then similarly for the y's, we have y to the 6th, and this is really y to the first power. So the base stays y, and you add 6 plus, there's really a 1 there. 6 plus 1 gives you y to the 7th. And then you're simplified completely. There are no negative exponents. You have one of each base showing, and you have your simplified coefficients. And we'll just do one more like that. Suppose I had 5a to the 4th, b to the 3rd, all raised to the 2nd power, times 2a b to the 2nd raised to the 3rd. These are very similar to the previous ones, except for now both of these are raised to a power. So we're going to simplify these individually. I'm going to do this without showing the steps. So I have 5 to the 2nd power. Come on, I can bring each of these to the power. So 5 to the 2nd power is 25 times a to the 4th to the 2nd power. Power to a power, remember you multiply. So this is a to the 8th. And then b to the 3rd squared, remember power to power you multiply. So this gives us b to the 3 times 2, which is 6. And you're going to multiply this by whatever you get for your result here. Again, 2 to the 3rd makes this 8. A to the 3rd, well, it's just a to the 3rd. B squared to the 3rd, power to power you multiply. 2 times 3 makes this b to the 6th. Once you have this, you want to multiply same bases with same bases and coefficients with coefficients. So 25 times 8, that comes out to 200. A to the 8th times a to the 3rd, remember multiplying things with the same base, you add their exponents, so that's a to the 11th, and then b to the 6th times b to the 6th, that's b to the 6 plus 6, which would be to the 12th. Again, you know you're simplified completely, you don't have any negative exponents, one of each base appearing, and coefficients simplified completely. The last part of this section that we'll talk about has to do with negative exponents. So for negative exponents, we already know one rule, right? So one rule that we already know is that x to the negative n power is equal to 1 over x, and then you make the power positive, right? So if you have a negative exponent, you move it to the denominator and make the power positive. But the other rule that follows from this, and we haven't talked about yet, is suppose the negative was already in the denominator. So let's say I had 1 over x to the negative n, so I already had a negative exponent in the denominator. what that really tells us is that we move it up to the other part of the fraction. So this is really x to the positive n. We usually put it over 1, but anything over 1 is just itself, so it's just going to be x to the n. So really the negative exponent really tells you to move it to the opposite part of the fraction. For the first rule that we had, the negative exponent in the numerator told us to move it down to the denominator and make it positive. For a negative in the denominator on the exponent, it tells us to move it to the numerator and make it positive. And that's really how we should think about the rule, because that'll make it a little easier to handle quickly in the problems that we solve. So we'll take a look at some examples here. So if I said to simplify, we'll do a few. If I said 1 over y to the negative 6th, well, this has a negative exponent in the denominator. That tells us that we should move it up to the numerator and make the exponent a positive 6. Now this is really over 1, but anything over 1 is just itself. It's really following from that second rule we just showed above. Similarly, if I had 1 over 2 to the negative 5, again, this is really telling us move this base of 2 to the numerator and make the exponent positive. So moving it up to the top, we get a positive 2 is the base, and then negative 5 as the exponent becomes positive 5, and then 2 to the 5th, that's your answer. You can simplify that. 2 to the 5th equals 32, which you can do on your calculator. But just making sure you understand how to get there. And then we'll do one more here. I think this one will really show you a little bit more about what this rule tells you. Suppose I had 2 over 3 to the negative 5 power. Now keep in mind what's going on. You have 2 over 3 to the negative 5. 2 and 3 are different bases, so you can't divide them or anything like that. So 2 is just going to stay 2. There's nothing else to do with it. It's in the numerator. It's going to stay 2 in the numerator. The 3 to the negative 5, the negative exponent on here tells you to move it up to the numerator. So this is 3 to the negative 5. Moving it up, the base still stays 3. So this is going to be times whatever this is when you move it up. It's 3 to the positive 5. Now, that's the answer, but you really have to simplify this. Now, 2 times 3 to the 5th, remember, these are different bases. You can't multiply them together. So it's 2 times whatever 3 to the 5th is, which ends up being 243. And then 2 times 243, if you multiply those together, that ends up giving you 486. And then that's your answer. But recognizing how this moves up, the 2 just stays 2, right? So you're going to leave it there. And 3 to the negative 5 moves up next to it as 3 to the positive 5 because it was in the denominator as a negative exponent. It tells you to move it up to the numerator. And we'll do a couple more here. Let's say I had a to the negative 5 over a to the 12th. Now there's a couple ways you can approach this. If I notice they have the same base, that means I can divide them, keeping the base the same, right? So if the base is a, the base is a, the base stays a, and then my rule for division of things with the same base tells me I subtract the exponents. So this would be really a to the negative 5 minus 12. So keep in mind when I say that, right? It's negative 5 minus 12. Now you don't have to show this, but it might be helpful to see it, because negative 5 minus 12 makes it more negative. It's a to the negative 17. And then, since I have a negative exponent, I haven't simplified completely. I want to make this a positive exponent. To make this a positive exponent, remember, negative here tells me to move it down to the bottom, so it's 1 over a and then to the positive 17. And then I've simplified it completely. Sometimes people approach this a little differently. You could start with the same problem, but instead of writing it as division right away, the first thing you might do is you might write this as, noticing the a to the negative 5 would move it to the denominator. Well, if you move it to the denominator, there's still something in the numerator, so it's equal to 1 over, and then you have a to the 12th, which is already down there, and then times a to the positive 5, because you moved it down in the denominator, it became positive. When you do that, you know, now you can just say this is 1 over, things with the same base, when you multiply, you add their exponents, a to the 17. Either way, you get the same answer. The first way is probably preferable because it uses the rules you know. The second way, you're moving around first and then using the rules you know. Either way is okay. As long as you get to the correct answer, it doesn't really matter. Let's take a look at another one that's similar to that. Letter E. If I say a t to the negative 4 over t to the negative 12. Well, using our rule, if I'm dividing things with the same base, remember I'm going to subtract their exponents. So this would be the base stays t, and then you have negative 4 minus a negative 12. Now the order matters. First off, it's a numerator minus the denominator. This minus sign is because you have to subtract the exponents. This is because the 12 is a negative 12. Well, what that leaves us with is if I have minus a negative here, this is really t to the negative 4 minus a negative really makes this negative 4 plus 12, which makes this t, and to the negative 4 plus 12 makes this t to the positive 8. Now, do I move this down? The answer is no, because it's a positive exponent. It just stays how it is. If I had a negative exponent at the end, like the previous problem, then we had to move it down to the denominator. But otherwise, you want to keep that as t to the positive 8 and leave it alone. Alternatively, you might have noticed at the beginning that the negative exponents can be moved to the opposite part of the fraction. T to the negative 4 tells you that's going to move to the bottom as t to the positive 4. T to the negative 12 tells you it's going to move to the top as t to the positive 12. So if you take care of the negative exponents first, that's okay. And you still have to follow your rules. If I have t to the 12 over t to the 4, the same base when you're dividing stays the same base. 12 minus 4 would give you t to the 8th. In this case, that was a little quicker because you could see it right away. It may not always be as obvious. So the last part of this section, we're going to talk about what happens when you have a fraction raised to a negative exponent. Alright, so fraction raised to a negative exponent. So suppose I have a over b, some fraction, raised to the negative n power. The easiest way to handle this is you're actually going to take the reciprocal of the inside, meaning flip it, right? So it's going to be b over a, and then you make the power on the outside a positive value, so positive n. And that's the rule. I will show you why it's true, similar to how we did in the previous ones. Suppose I started with a over b to the negative n, and I didn't know the rule above. Well, then that means I would write this as bringing the power to each piece inside. I could say it's a to the negative n over b to the negative n, right? Because that's a rule that we had, that if we have division or multiplication inside of an exponent, then you can bring the exponent to each piece. And now we know that if I have a negative exponent here, it tells you to move it to the opposite part of the fraction. So a to the negative n gets moved down to the denominator as a to the positive n. B to the negative n gets moved to the numerator as b to the positive n. And then this is just recognizing it. If I have b to the n and a to the n, that's the same as b over a all to the n, right? Because if I was to rewrite this as b to the n over a to the n. So that shows you that the rule is true. The easiest way to remember this, though, is if you have a fraction to a negative exponent, you flip the fraction inside, take the reciprocal, and make the exponent positive. We'll do an example of this just to make sure you see it. So if we said to simplify, and for this first one we'll say 2x to the third y to the second over 4x to the negative 2 y to the fifth, all raised to the negative 3 power. First thing to notice, All right, I have a fraction raised to a negative power, so that means that I'm going to do what the rule told me to do up here, which means take the fraction, take the reciprocal, and make the power on the outside positive. So basically write exactly what you saw. Don't worry about there's negative exponents in here. You're only worried about the one on the outside right now. So you write exactly what was in the denominator as the numerator. So we have 4x to the negative 2, y to the 5. Over the denominator is 2x to the 3, y to the 2. This whole thing now, remember that was a negative 3 before, becomes a positive 3 on the outside. You don't change anything on the inside while you're doing that step, right? You're just flipping it, but you're not changing the exponents or anything like that. Once you've done that, now we'll simplify the inside of this like we have in the past. So I'm going to write it as 4 over 2. We have x to the negative 2 over x to the 3 and y to the 5 over y to the second. It's all raised to the third power. And you don't necessarily have to show this part, but sometimes it's helpful to see it, I think. So simplifying this, 4 over 2 reduces to 2 over 1, which is just 2. X to the negative 2 over x to the 3. Be very careful here. You're subtracting things with the same, for exponents, if you have the same base. So negative 2 minus 3 makes us a negative 5, right? Think about it. It's negative 2 minus 3. To get you a negative 5 there as the exponent on the x. And then you have y to the 5 over y to the 2. Again, same base y. 5 minus 2 makes us y to the third. And then the whole thing is raised to the third power on the outside. We can simplify the inside of this now. Remember I mentioned it earlier. If you have a negative exponent on anything inside of here, it's going to move it down to the bottom. So everything's considered to be in the numerator right now. The negative exponent will tell you to move it down to the denominator. So this is really like 2y to the third. Those staying in the numerator because they have positive exponents. X to the negative 5 moves to the denominator as x to the positive 5. The whole thing raised to the third power. And then from here, we're going to raise each factor in here to the third power. So we'd have 2 to the third, y to the third to the third, over x to the fifth to the third. And we evaluate that. 2 to the third. Remember, it's not 2 times 3. It's 2 times itself 3 times. So it's 2 times 2 times 2, which makes that 8. Y to the third, that's y to the power. To a power, you multiply them, so it's y to the 9th. Over x to the 5th to the third is x to the 15th. So you get 8y to the 9th over x to the 15th. Remember, you know you're done because you don't have any negative exponents left in your answer. You have one of each variable showing up and you've simplified your coefficients completely. And maybe we'll take a look at one more here. So call this letter B. If I said I had 6x to the third, y to the fifth, over 2x to the 7th, y to the second, the whole thing raised to the negative 2 power. Remember the first thing you want to do, you see a fraction raised to a negative exponent. Let's make this the reciprocal on the inside and make the exponent positive on the outside. So flipping the inside, we have 2x to the 7th, y to the second, over 6x to the third, y to the fifth, all raised to the positive 2. And then I'll simplify the inside as I have in the past, but maybe I'll do it, without showing all the steps, because I think you can probably do that at this point. So 2 divided by 6, that reduces to 1/3. Make sure it's not 3, right? It's 2 divided by 2 gives you 1, 6 divided by 2 gives you 3, so it's 1/3. X to the 7th over x to the third, when you divide things with the same base, you subtract their exponent, so it's x to the 7 minus 3, which is 4. And then for the y's, y to the 2 over y to the 5, the base stays y. 2 minus 5, make sure you do it in the correct order, is negative 3. And then this whole thing is squared on the outside. Don't lose that squared on the outside. Sometimes people do. And then from there, I'll write this as a single fraction on the inside. Remember what I said earlier. If it's a positive exponent, it stays where it is. If it's a negative exponent, it gets moved to the denominator and becomes positive. So really rewriting this, in the numerator, I have 1 times x to the 4th, which is just x to the 4th. In the denominator, I have 3, because there's 3 in the denominator of the fraction. And then y to the negative 3 gets moved down as y to the positive 3 power. This whole thing is squared. And then remember what happens here. You're squaring each factor inside of here. So x to the 4th squared, power to a power, you're going to multiply. So you have x to the 8th. 3 to the 2nd power makes that 9. Y to the 3rd to the 2nd power is y to the 3 times 2, which is y to the 6th. And again, you know you're done. You only have positive exponents. You have one of each variable showing, and you have your coefficients simplified completely. So hopefully this video was helpful in understanding exponents, and thank you for listening.